Hi.
Good morning. Okay, welcome back. We are talking about multi-level modeling for longitudinal data. We're continuing with basics and overview, so continued from last week. Last week we talked about kind of contrasting MLM with other approaches that we might be used to working with, like repeated measures ANOVA and regression and so forth. We talked about the beginning stages, and today we're going to continue with the basics conversation by focusing in on the level 1 and level 2 models from the equations perspective. So just to do a review and kind of drive home the content, it's time for review. So why do we want to do MLM? What are the advantages of the method?
It takes account for the nested nature of some research in which people are nested within schools, and it accounts for that. It accounts for different levels.
Mm-hmm. Good, yeah, so it accounts for when you have potential dependencies in your data and the nesting, yeah. Other advantages that we talked about?
You get a sense of the rate of change over time.
So the flexible handling of time, yep, and we're gonna play around with that somewhat. I think in 2 weeks. What else?
Easier to handle missing data.
That's another really good advantage, yeah. Yeah, good. So you guys were sold or already sold before coming. What about the level 1 model versus the level 2 model conceptually? What's the difference? What's the key question we're asking for of the level 1 model? We also go ahead.
Level 1 parameters are often fixed parameters, right? So there's levels, or there's like values of that, and within those values there are level 2 parameters nested.
Level 1 parameters are often random parameters.
Right.
Random parameters, and so level 1 the level 1 model is interested in random effects. It's interested, another way to say that is interested in within person effects. In contrast to the level 2 model, which is interested in fixed effects or between person effects, right? So if we take level 1, we can say level 1 equals within person, because we're talking about longitudinal models, but it's within, I guess you would say, the nest, within nest, equals random effects, versus level 2 equals between person equals fixed effects. So that's sort of the quick, coarse way of remembering it. Yeah.
So I had them the wrong way around. But level 2 effects can be random effects, right? You can have confounders that are between subject effects.
Yeah, level 2 models incorporate level 1 effects. And you can also ask cross-level questions. So, yes. And when we get into the formulas today, that'll become clearer. What about the first 2 steps in MLM? So we talked about that last week as sort of the two key things that you would be doing initially.
You can run an unconditional means model to see if the nesting actually matters, and run like an ICC.
Yes, but I would call that the third thing.
Oh.
So we're going to talk about
Sorry.
that next week, basically. And we'll talk about it a little this week, but not really, actually.
Okay.
So
Take your
before
data,
we even start modeling, what do we do?
flip your data from wide to tall.
Yes, and then what?
Descriptive.
Or yes, exactly. And so actually you don't necessarily flip to run descriptives. You might do both. You might do a little of both, right? You might run some descriptives from a wide data set. You might run some descriptives from a long data set. But that's exactly it. You flip the data, and you also explore descriptively the time form of change. Okay. Any questions from last week? Any success stories? Did anyone like do a flip and start poking around, run a plot? Any questions? What about readings? Did anyone dig into the readings? There's some good ones there.
Oh yeah, other one works great. Yeah.
I did the data flip, but I tend to do it in R, so I didn't try it in SAS.
Oh.
I think we provided code.
And it worked?
In R?
Oh, because you pulled it from the Singer and Willett website.
I
The-
just,
Figured it out.
yeah.
Okay. All right.
But I did not try the code that you provided.
Okay. Well, as long as you get there, that's all that matters. Okay. So, continuing on. So, we're going to have a couple examples today, but we're going to start by continuing with the National Youth Survey as the example. This was a longitudinal study. Both kids and parents were interviewed. It was interested in both sort of positive and negative behaviors, so deviant behaviors, resiliency, etc. The variables that we talked about last week and that we'll continue to talk about were age, and that's 5 waves of data, so ages 11 to 15. Sex, and this was coded as male equals 1. Tall, or tolerance for deviant behavior over time, and exposure to deviant behavior at age 11, or on or before age 11. So, as yet another quiz, do we think that age over 11 to 15 is a level 1 or level 2 variable? And we can contrast that, say, with like comparing it to, say, sex. Level 1, right? Because we can have it on both level 1 and level 2, but substantively how we're thinking about it is the within person change in tolerance for deviant behavior due to time, right? Is this linear change, quadratic change, etc.? Change at all, right? Is there a slope at all? Would be, I think, the first key question, particularly in this study. Versus sex is level 2. And then what about exposure to deviant behavior at age 11? Level 2, that was treated as like, did you have the exposure or not? And then tolerance for deviant behavior over time is our DV. Good. So then just looking at the 2 data sets, we see, just as a reminder, the difference. 3 observations here versus observation number 9, and then 2 of the records for 45. So this would be continued down. It's just cut off. Our age variable, tolerance variable, male, and exposure. So for person level versus person period, which is which here? And we also say long versus wide. We also say stacked versus unstacked. Which is the person level data set? The top one, the wide one, right? Because the rows are people versus person period. In this case, the rows are the time points. So observations by time points. So long versus wide, stacked versus unstacked. So any questions on that? No? Good. All right. So as a review, random versus fixed effects. Random effects, we're generally not trying to draw inferences about them. I say generally, that's really changing, particularly for those of you who are doing EMA type stuff. You're going to be potentially doing all sort of level 1 questions, right? We assume, though, conceptually, we're assuming that variation is due to random sampling. Some key questions at level 1 that we would ask are, what are the level 1 growth parameters? So the randomly varying intercepts and slopes, and we think of them as a random subset of a set of individual growth parameters from the population of interest. Versus fixed effects, we're generally intentionally making inferences here. We can have categorical or continuous. So example of categorical would be like, say, treatment condition. We have the example of sex in the youth longitudinal study. It could be age, but when I say age here, it's like age as a static covariate. Like, for example, a level 2 question could be, what is the effect of an adolescent deviancy treatment covarying for age? So you might have an idea or a thought that that age, when you receive treatment, is important to the treatment effect, or in the sense that you would want to control for it, or even do, like, say, an interaction term and look and see if it's better for young kids versus, young adolescents versus older adolescents. Just a word on nests, because I try and come up with like little rules of thumbs that actually boil down, oversimplify the information, but they make it memorable. So something that might help you think about, like, keeping the nest straight, is that something that's we're used to, like, it's easy to think about, say, the student egg nested within the school nest, right? Or doctors or therapists and patients nested within them, right? But when we move into longitudinal data, that's where we actually flip it, right? And the person becomes the nest, and the repeated observations are the eggs in the nest. Okay, that was a last-minute addition. Hopefully, you like it. Okay, so then we started exploring intra-individual change. So what we have here is the tolerance for deviant behavior. We have age here, and so the idea was to look at this descriptively and make a guess or have a thought on what might be happening. So, with the relationship between age and tolerance for deviant behavior, what was the sense that we got of the thought? What do you think's going on in terms of the functional form for time?
As you age, you get more tolerant of deviant behavior in general for most people.
Ever so slightly.
Ever so slightly.
Yes.
But the rate of change do differ by individual.
Yes, so that's exactly it, right? You see a slight positive slope with a lot of variability, or a fair amount of variability. This is the same picture, or the same information. It's just a smooth versus unsmooth spaghetti plot, but the message is the same, right? You see a slight positive linear slope, and you see some variability. You can also think about this in terms of what are the components of what's going on here, the sort of core level 1 predictors of individual change. And so we've got the intercept here, right? And then the slope, and this is the predicted slope here. And then this would be an example of one error term, right? So one error term of the predicted slope for across individuals versus this one bad kid over time, right? So I are the lines and J are the time points, right? I's are individuals and J's are time points or students or patients. Am I saying that right? So if we had kids nested within schools, the J is the school. No, the J is the kid, and the I is the school. Is that right? I'll think about it more, but I'm pretty sure that's right. But that's just a simple, like, whole nesting thing that actually does get a little bit confusing. Okay, that was it. All right, moving on to level 2, between group differences and change. We actually have 2 questions here, right? We have by sex, and then our second question, we took a continuous predictor and turned it into a categorical predictor. So this is low exposure to deviant behavior or deviant, I think it's deviant peers or deviant behavior, on or before age 11, and high exposure. And so the question then is, does the intercept and or slope differ, the intra-individual intercept and or slope differ between sex? First question. Does it? What do we think? So looking at differences in the intercept, differences in the slope between males and females. No, right? It looks like potentially more variability in intercepts for males, more variability in slopes for females, but on a whole, it's kind of the same story. And then what about low versus high exposure?
Yes, there's an interference in this.
Yes, and is it both intercepts and slopes or just slopes?
Just low.
Right, it's looking like that, right? It's looking like this is pretty much the same amount, but that our steepest slope is those high exposure kids, right? Of the 2 questions, this is the one where we're like, okay, there might be something going on there. What else? This is just the spaghetti plot code for SAS. SPSS, SPSS isn't so great with graphics. I don't really use it for graphics, so I don't have the other one. But we've got proc SG panel. The data set is called tolerance _ person period. You're just asking for no auto legend, no legend, default legend. Panel by male, which is the variable name. In this case, it's not called sex. Plot regression for age by tolerance. Okay? Any questions on that? Okay. I'm basically going to say the same exact thing 5,000 different ways for 1 hour. So, we're continuing on to look at it a slightly different way. So what we have here is we have gender differences in delinquent behavior among teens. We're looking at it from 2 perspectives. We're looking at one kid. This is ID 994001. And we're looking at their individual intercept and slope from the equation's perspective, right? So, predicted tolerance for deviant behavior across I kids and J occasions, and the J occasions are ages 11 through 15, is equal to the intercept for I kid, and in this case I kid is case 994001, right? Plus the slope for age. This data set has age centered at 11, so we're starting at age 11, right? We're not starting at 0. And so this is the slope for age plus the error. And then the picture shows, you can just see that there is, this little bit of error here. These are the bits of error. So that would be the equation for one kid, but that's the equation for all kids at level 1. Okay? So level 1 modeled the average individual change trajectory. This describes how each person's outcome depends on time. Right? In this case, it could be depending on other things, but we keep talking about time for the most part. And then for those of you who do have other nesting questions, you can just, okay, I've got this, and we can make the translations too. So then what's going on, what's the difference with the level 2 model? The difference with the level 2 model is that your 2 key level 1 parameters become outcomes in the level 2 model, okay? So you've got the intercept for kid I, right, or across I kids, is equal to intercept plus slope, and now we've got a between person question plus error, right? Versus the slope question, we've got slope for male plus error, and we're going to go over it again. But for the message here, in terms of what are we thinking about, we've got girls in red, boys in blue, and we're asking the same question: do intercepts and slope differ by sex? How do features of individual trajectories, intercepts and slopes, vary by between person characteristics, for example, sex? Okay? Let's see if there's anything else. Okay, so this is kind of a sidebar, but not completely. But we did start talking about correlation structure last week. And so I thought that we could just ask the question of, what is the covariance structure for this particular data set. So what we have here is just a correlation matrix of tolerance by tolerance over time, right? Ages 11 to 15. And we talked last week if we were running a repeated measures ANOVA, we would assume an exchangeable correlation structure, or also called compound symmetric correlation structure. And what that would argue is that the adjacent time points, the magnitude and direction of the correlation coefficient of adjacent time points are equal, right? And we talked about how for some studies that's a reasonable assumption to make, and for other studies that is not a reasonable assumption to make. So in this study, is it a reasonable assumption to make? Age 12 to age 11 here, 0.65. Age 13 to age 12, 0.24. Age 14, 13, 0.58. 15, 14.82. No. Okay. So, and Ron talked about how it's often an unstructured. You can make it. You can specify in the code unstructured, and that's just telling SAS or whatever program you're using. You tell me what you put in the parameter estimates for all of the correlations for the adjacent time points. So you might want to do that here, because it's like this, right? It's not going down or up. There's not like another potential form that you could fit to it. It looks like you need to just have it fit for you. I don't know what Ron does. When I do MLM, I usually just leave it at unstructured. Whereas when I do GE, I tend to change it based on what I think is going on. But I don't know if there's any advantage to doing it that way. It just seems to be how I do it.
Yeah, I always
Do you
leave
just
it
leave it
at
unstructured for GE as well?
I've never done GEE in my life.
Okay. Yeah. So so then there's no systematic reason why I do that. Then.
Can you check for model fit, compare model fit?
By
Looking at the model fit to the same model
Structure
fit with
versus
two different
unstructured.
structures.
yes.
See.
Yeah, you definitely could do that. Although, I guess you would assume that if you're talking about with MLM,
Yeah.
I guess you would assume that if you do it unstructured, that's going to be the best.
Mm-hmm.
But at the same time, my understanding is that you are burning degrees of freedom by doing it. So, okay, so that was a little sidebar, but I guess the message is that if you're used to GE versus MLM, that this is still going on with MLM. It's modeling the random effects, but you are still imposing a sort of functional form to the covariance matrix. Any questions on that? What's the take home? I guess leave it on unstructured. Yes.
Is that the difference between plotting something that is linear or freely estimated? Or what is the implication of assuming a structured or unstructured covariance matrix?
It has to do with the dependencies, so it's kind of separate from time. Well, I guess let's see. If you thought it was linear, you might think it was AR1, right? Because AR1 is autoregressive, so AR1 is going to go down over time. So I guess, yeah, I don't think I can effectively answer that question, but to say that they probably have something to do with each other.
Yeah, the thing we know best is that autocorrelation over time, and it typically decreases, so you get a structure where the diagonals are more or less the same as you move up or down from one, and they get decreasingly smaller. That's the structured variant that we tend to know in the kind of research we do.
Right.
If you're doing a treatment study with 6 follow-ups, you'll get typically a nice structured autoregressive pattern.
And that would be a linear, and
Yeah.
that would be a linear effect as well. Sorry.
Yeah, I presume you could get well, it depends what you mean by linear, but you could probably get a quadratic type effect that's increasingly less correlated or increasingly more correlated, but it isn't, it isn't a linear trend, it's more of a curvilinear trend.
So what are the consequences for the amount of parameters in the estimated model? Are the covariances included as weights for the individual indicators, or is there no difference in the amount of estimated parameters?
Weights.
It's not so much weighting, but I believe the way structured saves degrees of freedom is that you can make some assumptions about the matrix where you have fewer computational elements and therefore save degrees of freedom. So if, this is a bad example because it's really unstructured, but you could, if you go one up from the diagonal ones, if you made the assumption that 0.65, 0.24, 0.58, 0.82 were equal, you could save computational elements and preserve degrees of freedom. And that makes, if the model fits well, it makes the computations more efficient.
Thank you. That's helpful to me. Okay, so moving into level 1 and level 2 model basics. Level model is the model that reasonably approximates the processes that are occurring. Typically, we're looking at the intercept and linear change. When a common functional form for time has been fit, then individuals can only differ in the values of their growth parameters, right? Plus error. And once we fit that form for time, our next step is looking to start shrinking those level 1 residuals, right? Are there level 2 parameters that can, or level 2 variables that could make these level 1 residuals smaller, right? So that's essentially what we're doing, and what we're going to do next week when we start doing, starting with the unconditional means model, adding the slope for time, moving on to the 2-level model, and so on. So the level 1 model includes structural and stochastic part. The structural is each person's true initial status and the slope of the individual change trajectory, plus the error, right? The error for the person across J time points or across J observations. So in terms of the example that we've been working with, this is the same information as the last slide. It's just, this is from the Singer and Well website. It's got better colors, and it helps you track it a lot better. So growth in, this is a different a different example though. There's 103 African American infants from low-income families, half randomized to early intervention. The DV here is cognitive functioning, right? And the J is 3 time points at 6-month intervals. So this is starting from age 1 and going to age 2 at 6-month intervals. So that's the difference here of what we're working with. Okay? So the structural portion embodies what we think about in terms of the shape of the true individual trajectory in the sample. So in this case, infant cognitive growth, right, on average. And so that is comprised of the intercept for the kid's eye, and then the slope for age, and here we've got age centered at 1, right? So the intercept of the true change trajectory, true initial status at the true value of cognitive age 1, starting place, plus slope, plus here are the error terms. You can see them a little bit better in this picture than in the last one. So step 1, fit a linear function for age, characterized by cognition at age 1 and the incremental change over 3 years. And we're going to add the effect of program to the level 2 model. So does infant cognitive development differ by whether or not they get this early intervention program? So we're moving into the level 2 model. The level 2 submodel must be written in 2 separate parts, a model for the level 1 intercept and a model for the level 1 slope. Then each part will specify a relationship between the individual growth parameter and a particular predictor. In this case, we're going to talk about the early intervention programs, while also allowing for leftover random error. So this is what our level 2 submodels look like. So we've got the level 1 intercept. The intercept for non-program participants, so intercept non-program participants, plus the increment in the intercept for treatment participants, plus the error in intercepts. The second part of the level 2 model is the model for the slope. We've got the slope for non-program participants, plus the incremental difference in the slope for program participants, plus the error. Okay? Okay. Errors can be correlated. Level 2 residuals are assumed to have a bivariate normal distribution. This is again a similar pattern where we've got the equation. I walk through it and then I show you the equation again from the Singer and Willett website. So I'll come over here. But when you follow over, you can see we've got the population average true initial status for non-participants. Okay, so in this case, these are infants who have not received the program. What is their initial status at the age of 1 for cognitive development? The difference in the population average true initial status between participants and non-participants. So the incremental difference due to program, whether the infant's receiving the program. And that's for the level 1 intercepts. And then for the level 1 slopes, we have the average rate of change for the non-participants and the incremental difference in rate of change for participants. Okay, so the key to remembering the subscripts is that the first subscript indicates the role in the level 1 model, second indicates the role in the level 2 model, right? So intercepts, and then we think about this in terms of like, well, we have a dichotomous outcome here, so it's easy to interpret because we can say, okay, this is program versus no program. Program being coded as 0, no program being coded as 0. Okay? Make sense? Yeah? Okay. Mm-hmm.
Are there zetas unique to both the level 2 model and the level 1 model? Are those distinct zetas?
Yes. I think, although I'm yes.
Oh, yeah.
They're modeled, they're gonna be modeled, there are zetas due to intercepts, zetas due to slopes within person and between person. And when we get into the output, we can look at all of those different pieces. And we look at how we affect them too by adding in predictors.
Right, so there's the individual estimate for instance, the intercept. Then you use certain predictors of the intercept, and whatever variance is not explained by the predictors of the intercept would be attributed to the zeta for that individual at the second level.
For that individual at the second level,
For at level 2. So within that individual having a specific value for his intercept relative to the rest of the population, there would be certain between subjects effects that explain that difference in intercept, and whatever individual difference in intercept is not explained by those predictors would be the residuals for the level 2 effect.
yes. Okay. Okay.
And then the residuals for the level 1 effect would basically just be the misfit for the linear model.
I mean, it will take me 10 minutes to think about what you just said. And then I can answer your question. Sorry. Does Ron know?
But if I'm following what you're saying, I think essentially what you said is correct.
And when we get to that, I think it's easier when we get to the output, because then you can be like, okay, here, here's the piece left over from this part of the model versus this part versus this part.
Yeah. And if you think about how would you descriptively present all of the information from a multi-level model, you essentially have individual patterns, in this case, individual patterns over time, which, that's the spaghetti plot-like stuff, and that's where all of the level 1 error rate of change, zetas, would come into play.
Here and here.
And then you would have a rolled up group effect that aggregates over individuals, and that's where the top error would come into play. We can't envision both of those things at the same time ordinarily, which is why this multi-level stuff makes our brains explode.
Yeah. Yeah, I find that I need to walk through whether it be the formulas or the output or even the code, and continually make the connections between those three kind of sources of information.
Yeah, if we were statisticians, these equations, that would be intuitive to us.
Mm-hmm.
For those of us who are essentially behavioral researchers and we're at best applied data analysts, the gears have to start churning, between the ears until the smoke starts coming out, and then we can sort of grind through what it means.
But in my mind, because I'm not big on formulas as a way to understand things, but this is the one method where it's important. In my mind, where it helps me at least, whereas there are other instances where the formula doesn't necessarily help me conceptualize it. Here's a picture, though, that helps us to conceptualize it. Just keeping in mind that this is the incremental, when we are looking at these parameter estimates, we're thinking about the incremental difference from here to here, okay? But this is just putting it into a form that we're used to looking at. And then plus the error, which, way back when, sort of the reason why I put this here. Okay. So this is looking at the composite model, so making all of the translations into the full composite multi-level model. Here's the same thing, but with arrows to help us trace where things are going. So starting from the two subcomponents of the level 2 model that fit the level 1 parameters, coming down into this model and this model, which is essentially the same thing, just kind of breaking out the different interaction terms and so forth. In this example, we've got children of alcoholics by time, so we've got a cross-level interaction here, right? So this is back to the children youth survey, and the say, I don't know what the outcome variable is in this example, but we could just say it's tolerance for deviancy, or we could say it's growth in substance use over time. Time is still going to be that age 11 to 15, but the categorical level 2 predictor here is the COA, I believe, stands for children of alcoholics. So that gives us the cross-level interaction of within person age by between person children of alcoholics, whether or not you were one. Questions. So that what we've done is we've walked through from 1 to 2 to the 2 submodels of level 2 to the composite model, and then finally to this example here that gives us a cross-level interaction. Any questions? Go for it.
So is the estimated amount of parameters for the two, I'm thinking about the models combined, what the estimated number of parameters is. And leaving aside whether it's like structured or unstructured, would it, for the red part here, be the product of the amount of indications for time by the amount of predictors in the red part, like the level 2 red part?
You mean just the two condition, like say COA versus not times 5 time points?
Yeah.
Yeah. Yeah, and then, and thinking about, you know, the sort of, we can now think about this as main effect for time, main effect for COA by time interaction. So if we were putting this out in our code, that's, you know, that's like the model that we're used to looking at or used to writing out. Does that answer the question?
Yes.
Okay. Other questions? All right, so those are some Singer and Willett examples. One of the main examples I'm going to work with is actually the example that I inherited from Chris Kaler, because that's who I inherited this class from. So the reading for next week, there's a paper that this slide is based on, but then next week when we start getting into like iterative model building, where we're starting with unconditional means, adding in the slope, so on and so forth, and looking at incremental changes in all of the different parameter estimates, we're going to be working with this data. So this data is a smoking study, and it is the SPOMS variable is I guess profile of mood states, and so it is a depression mood in relation to quitting smoking in a smoking trial, and the time is baseline and then 1 through 3. We've got 0, 1, 2, 3. So here's just an example of looking at change descriptively, right? It's not a plot, it's a table. But this is their SPOMS, so their profile of mood state scores over the 4 time points. So it says 1, 5, 6, 7, 8, but it is 0, 1, 2, 3, right? So even just looking at this, do we think we have a linear change in their mood state in this smoking trial? right? They're going from 0.65, then they go up, then they go down, and then actually, sorry, I should do this. So just here. So not exactly linear, right? And so potentially quadratic, negative quadratic, but as we move into this, we'll see the fancy thing that Chris did to deal with it. This is looking at the correlation between the different observations for time. And then here is the sample SAS code. And this is the sample. So I've annotated the code. By next week, I will have played catch up and added in the M+. But for right now, this is just now. We're gonna go through each step, and we'll have the code, and we'll have the output, and we'll have the formulas all together. But this is just kind of driving home what we've talked about today and translating it into the syntax form. So for SAS, it's proc mixed. The data set is called the POMS data set. Oh, actually, I think there's we've got full estimation, maximum likelihood. This is just like a no class print. It's just asking us, we don't need to print like the information for what's in the classes, which would be, in this case, the class is time and what's in it is the people. Print the parameter estimate information. This is something that Chris put in here. It's just that he wanted people with greater than one observation. And then the class's ID. And so here's just like sort of an annotated version of the model statement, right? Model the outcome, which is mood, due to time. And on the random statement, we have both intercept and time. And we've got type unstructured, subject ID, run. So this is giving us this. Okay? This is the same thing without the annotation. This is SPSS, so it's called mixed. Here's our mood dependent variable with time, so that's our model statement. Here's our print statement. What do we want to be put out in the output? SPSS is restricted maximum likelihood estimation, so it's a different estimation method, slightly less powerful. So you could, maybe if you weren't getting your model converging in SPSS, you could try SAS and see if it worked. We've got time on the fixed effect statement and intercept and time on the random statement. Here's our ID and code type unstructured. Okay? So that would be the SPSS code. And then this is just an example without the annotation. That's just sort of to get your feet wet in making the translation between the formulas and the syntax. But like I said, we'll do them one by one next week. That's all I have. Other questions?
I guess when you talk about readings and stuff, those are on the website, I assume? Sorry, I wasn't here last week. So.
Oh no, that's okay. Yeah, so the DPH, the 9 a.m. seminars website,
Okay.
they're good, I mean, I think they're good readings.
Okay.
And I started pulling together some M+ stuff that I put in next week's.